Good morning to all of you. Today we will see a design problem of butterworth digital filter. In this problem we are going to see how to design a digital butterworth filter from the given specifications using bilinear transformation. Okay, this type of problems are very common to appear in the university examinations, semester examinations. Okay, so therefore you concentrate more on this and you practice more problems, then you will get all these things very easy, so that whenever in the exams if it appears easily you can do it without any errors. If you practice it, you will get the correct way of and easy way of doing the things. Okay, now see, design a digital butterworth filter satisfying the constraints. So these are the important things. Constraints 0.707 less than or equal to magnitude of h of e power j omega less than or equal to 1, and from 0 to pi by 2. 0 to pi by 2. Whenever I am reading this, just to concentrate on the problem. Later we will discuss the solution. Okay, design a digital butterworth filter satisfying the constraints. So 0.707 less than or equal to magnitude of the transfer function of the filter less than 1 for 0 to omega by 2, from 0 to omega by 2, and less than, and this value magnitude of h of e power j omega less than or equal to 0.2 for 3 by 4 less than or equal to omega less than or equal to pi. Okay, these are the given constraints or specifications with a t is equal to 1 second. Okay, what is t? T is the sampling interval that is given 1 second. In some problems you will be given t, or sometimes assume t, sometimes t will not be given. In that case also you have to take t is 1 second. If at all, if it is nothing is given about t, just to take 1 second to solve the problem. Otherwise, if t is not given, just you can calculate using the given specifications. Most of the times t will be given. Most of the times t will be given directly in the problem. Otherwise, if any other value of t is given, just you can take that and using bilinear transformation. Okay. Now we will see this. We will try to understand what are the given constraints or specifications. You see this, from 0 to pi by 2, magnitude is 1. You have to understand the filter nature also. Okay. Suppose see, if this is the magnitude characteristics of a given filter, what are the specifications given? 0 to pi by 2, it is, what is its magnitude? It is 1. 1 from 0 to pi by 2, its magnitude varies from between 1 by root 2 and 1. Okay, 1 by root 2 and 1. You assume that this is pi by 2 and this is pi by 2 and pi. This is the omega domain. Now what is the meaning of that? In between this 0 to pi by 2, its magnitude varies between 1 by root 2 and 1. Okay. So therefore this is maximum is assumed 1 and this is something 1 by or root 2. 1 by root 2 means 0.707. Okay, like this, magnitude characteristics like this, and from 3 by 4 to pi, 3 pi by 4 to pi, it is less than or equal to 0.2. So therefore pi by 2 and it varies, you assume that it is something like this. So therefore, by understanding this, what you can, by looking at this characteristics, what you can understand is, it is a which type of filter is this one? It is a, see, at low frequencies its amplitude is maximum, and at high frequencies amplitude is reducing slowly. Okay, that is why we can say that it is a low pass filter. Low pass filter. So most of the problems are in the examination, they appear as a low pass filter problems. So that is why I have taken this. So therefore, what you have to understand is what type of filter. Sometimes filter also will be given, low pass filter like that they will be given. But and high pass filter also like that they will give the they will mention the type of filter. Suppose even if they did not given the details from the given specifications, we can understand that it is a what type of filter. From this we can say that it is a type of low pass filter type. Okay, the given filter is a low pass filter. Now coming to the specifications, now we have identified so what type of filter it is. Either it is low pass filter, high pass filter or any other filter. You can understand from the given specifications. Now so you come here, see if you remember the characteristics of butterworth filter, butterworth low pass filter or butterworth filter characteristics, it looks like this. See the characteristics of butterworth filter are like this. This is actually magnitude is 1. This is 1 by under root 1 plus epsilon square, and this is 1 by under root 1 plus lambda square. These are the two different parameters. And epsilon is the pass band parameter, lambda is the stop band parameter, like that. They will be, so you have, they are not given here, but using this specification, so we have to understand that what is the value, what is this and what is this. Okay. Now coming to this, we take, see, this is the pass band. This is the pass band characteristics from 0 to pi by 2. It is a 0 to pi by 2, it is a pass band. So pass band parameter means 1 by under root 1 plus lambda epsilon square. That is, what is that value given? 0.707. Okay, that value is given. And other thing, you see this. This is 0.2 between 3 pi by 4 and pi. So therefore, and this is what is that value? We'll get. So stop band parameter. So therefore 1 by under root 1 plus lambda square is equal to 0.2. So what you have to understand from this diagram is it is a low pass filter characteristics of a Butterworth filter. From this Butterworth filter, so we can get these values. So here, see, this is 0.707 is 0.2. So this is the starting 1 by under root epsilon under root 1 plus epsilon square, and this is 1 by under root 1 plus lambda square. Okay, where epsilon is the pass band parameter and lambda is the stop band parameter. Okay, now see, this is omega p, pass band edge frequency. Already I told you this is the pass band, this is the pass band edge frequency, and this is the stop band edge frequency. Okay, so if you see this is the pass band edge frequency and this is the stop band. So from here it is a pass band. Okay, entire this thing is a pass band, this is a transition, something like that. Stop band. So edge frequencies are given pi by 2 and 3 pi by 4. So why these are not the edge frequency? This is not edge frequency. It is the final value. Okay, but you have to consider this is the beginning of the stop band omega s, and omega p is the ending of the stop band. Okay, omega p is the end of the stop band. Omega s end of the pass band, and omega s is the beginning of the stop band. Like that you have to take the two parameters. Okay, now, so we have the 1 by under root epsilon square, 1 by under root 1 plus lambda square, stop band, pass band edge frequency, stop band edge frequency. These are the parameters required to design the filter. Now see, we have to calculate. So pre-wrapping frequencies omega s by omega p. Omega s is the analog stop band edge frequency. Omega p is the analog pass band edge frequency. We know that omega s is equal to 2 by t tan omega s by 2. Omega s by 2. This is the stop band edge frequency. This one, and this is the pass band edge frequency pi by 2. So therefore the ratio we have to find out. That ratio gives you the what is the pass band edge frequency, stop band edge frequency and pass band edge frequency in the analog domain, because we have to design first analog filter transfer function. Okay, so therefore if you substitute that in the place of t, actually t is 1, omega s is 3 pi by 4, and already 2 is there in the denominator, so therefore it becomes 3 pi by 8 and it is pi by 2 divided by 2. Okay, just you substitute omega s value and omega p value and you divide those values by 2, then 3 pi by 4 and pi by 4, tan 3 pi by 8, so tan pi by 4 you will get, and if you simplify that, 2 tan 3 pi by 8 divided by 2 tan pi by 4, so pi by 4 is 1, tan pi by 4 value is 1, and if you simplify that you will get 2.414 as this ratio omega s by omega p. Now generally order of the filter in terms of lambda and epsilon you can calculate this. This is an important formula, so you have to remember this one. Okay, so order, if you want actually to design a filter we need the order. So what is the order of the filter? To calculate that order, n must be greater than or equal to log lambda by epsilon divided by log omega s by omega p. Okay, already we have calculated this value, this omega s omega p ratio, and lambda and epsilon values you can calculate from these two relations. Okay, so suppose if it is given in terms of epsilon and lambda like this, you can get it. Sometimes directly you will be given in the pass band attenuation, stop band attenuation, you will be given. In that case we have to use a different formula that later I will reveal that, I will give you. So now, so to get that, to get what is epsilon and what is lambda, so 1 by, see here is right, so 1 by under root 1 plus lambda square is equal to 0.2. So if you take the square of this on both sides, what you will get, 1 by 1 plus lambda square is equal to 0.2 whole square. So 1 by 0.2 whole square is equal to 1 plus lambda square, like that. Lambda square is equal to 1 divided by 0.2 whole square minus 1, and 0.2 into 0.2 is 0.04. Okay, 1 by 0.04 means you will get some value, and if you take the under root of that you will get so lambda value. So the lambda is 4.898. Okay, so you can calculate in this way. After calculating this, you take the square root of this 1 by 0.2 whole square minus 1. Okay, you will get 4 values. Lambda value is 4.898. In the same way, you can calculate epsilon. Okay, what is epsilon? Do that. So 1 by under root 1 plus epsilon square. This is equal to, so 1 by root. So 0.707 we can write it as a, so 1 by root 2. If we take the square on both sides, 1 by 1 plus epsilon square is equal to 1 by 2. So therefore 1 plus epsilon square is equal to 2 if we take the cross multiplication, and so epsilon square is equal to 2 minus 1, epsilon is equal to, epsilon square is equal to 1, epsilon is equal to under root 1, generally we will take plus 1, plus or minus 1 we will get plus 1. So therefore epsilon value is 1. Now lambda is 4.898, epsilon is 1. Now using these two values, epsilon by lambda, lambda by epsilon, you see this equation for order, log lambda by epsilon means log 4.898 divided by log omega s by omega p. Omega s by omega p is 2.414. So you will get 1.803. If you simplify this, it is approximately 2. Okay? Because order must be an integer. Order never becomes a fraction. It must be an integer. So that is why we will take the nearest value, that is 2. So therefore, now we got the second order filter. Okay? After calculating n value, we have identified that it is a second order filter. Like that you can find out third, fourth order if it is given in the relation. So therefore, after this we have to find out this cutoff frequency. Cutoff frequency in analog domain, omega c. That omega formula for that is omega p divided by epsilon power 1 by n. So it is because see here n is 2. So omega p divided by epsilon, that is 1 power 1 by 2. Again it is root 1 is equal to 1 only. That is why we take omega p only. Okay. Omega c is the omega p. Okay. Cutoff frequency is equal to, so pass band edge frequency, because epsilon value is 1 here. So that is why we take it. And now that omega c 2 tan omega p by 2. So cutoff frequency you can calculate using 2 by t tan omega p by 2. So here t is 1 given in the problem. So therefore t 2 by 1, this is 1, 2 by 1 tan pi by 4. So pi by 4 is value is 1. So 2 tan pi by 4 means 2 into 1 is 1. Okay, now we have calculated. So this ratio, order, especially this order is important. Calculating the order is important. After calculating the order, we have calculated the cutoff frequency also. That cutoff frequency is 2 radians per second. Okay, in analog domain. Now what to do is, we have identified everything, right? Whatever the prerequisites to design the filter. Now see, it is a second order filter. We know that. Therefore, the second order normalized Butterworth filter transfer function looks like this. This is a standard representation. So we have to understand that. So 1 by s square plus root 2s plus 1. Okay. So for the first order, it is 1 by s plus 1. For second order, this is the 1 by s square plus and the root 2s plus 1. Okay, like that for third order and fourth order, I will give you what are the standard transfer functions. Okay, this is h of s and omega c. See, h of s for omega c is equal to 2 radians per second is obtained by substituting s is equal to s by 2 in h of s. Okay. First of all, this is the analog filter transfer function, standard analog filter transfer function, and we have written this from the Butterworth standard transfer functions, which was already predefined. So therefore, for cutoff frequency omega c is equal to 2 radians per second. If you want to find out, just wherever s is there, you substitute s by 2 in given h of s. So h of s is given, you substitute s is equal to s by 2, then what you will get? h of s, like analog filter. h of s means just for analog to represent the difference analog. So 1 by s by 2 whole square, because s is there, root 2 s by 2 whole square plus 1. Here you will get s by s square by 4. Here root 2 by 2 s square plus 1. Okay. So therefore, if you take the LCM and if you simplify this, you will get, so 4 by s square plus 2.82s plus 4. Just by taking, see, here it is s square by 4 plus root 2 by 2 into s square. Sorry, this is a square is not there here. So s root 2 by 2 s plus 1, square is not there. So you will not get square. So therefore, if you simplify this here, LCM you will get 4, and if you simplify that, you will get the answer. Okay. So therefore, this 4 comes upside, because LCM is 4. This 4 gets upside. 4 divided by s square plus 2.828s plus 4. Okay. So that is the analog filter transfer function. Now it is simple. We got the analog filter transfer function using the cutoff frequency. Now we have to use a bilinear transformation. Okay, that is important. Also in the problem they will give you using a particular method. Here that particular method is a bilinear transformation method. So in bilinear transformation method we know that, so to design a filter using bilinear transformation, so we have to substitute in the wherever s is there, we have to substitute 2 by t 1 minus z inverse by 1 plus z inverse. Suppose see, I want to design a filter h of a digital filter hz, and that hz how to design it, I will find out the first of all analog filter transfer function. In that analog filter transfer function I substitute s is equal to 2 by t 1 minus Z inverse by 1 plus Z inverse. Okay, like this. So that is what I have written here. H of Z is equal to H of S, HA of S at S is equal to 2 by T, 1 minus Z inverse by 1 plus Z inverse. Now see, what I will do is, wherever S is there in the equation, I will write that 2 by T, 1 minus Z inverse by 1 plus Z inverse. Okay, so here T value is 1. Okay, sampling interval is given in the problem, it is 1 second. So therefore 4 divided by, I am continuing from this, 4 divided by, so what is S? S is equal to 2 into 1 minus Z inverse divided by 1 plus Z inverse, because T value is 1. Okay, T is 1, even if you write or not, it is not a problem. And after that 2.828, yes, in the place of S, just to substitute 1 minus Z inverse by 1 plus Z inverse plus 4, like this. And you take LCM here, you take LCM, and if you simplify that, so you will get finally this H of Z. Okay, take LCM. What is LCM here? 1 plus Z inverse. That 1 plus Z inverse goes to the upside. So there we see 1 plus Z inverse, actually square is there, right? Square is there. S square. S square means 2 1 minus Z inverse divided by 1 plus Z inverse. So therefore, what you will get? You will get LCM in the denominator. You will get LCM as 1 plus Z inverse whole square. Okay, so therefore this denominator comes to the numerator if you manipulate it. So then what happens? See, 2 into 1 minus Z inverse whole square you will get, and already 2 is there, that is why you will get 4. Like that, what happens is, so you will get this function 4 into 1 plus Z inverse whole square divided by 4. So that 4 comes all the way. So here also 4 is there. So therefore, what is the here 1 plus Z inverse whole square. So that 1 plus Z inverse whole square, it comes here as a product term. And finally, if you simplify that, if you take some common value here, if you simplify it, you will get. So these things will not modify. Try to understand. So 1 plus Z inverse whole square. So here also 1 plus Z inverse whole square. And by expanding this, so 1 minus Z inverse whole square, 1 minus Z inverse whole square, here 1 plus Z inverse whole square. If you expand this, what you will get is, you will get finally, this is the transfer function of digital filter, required second order Butterworth transfer function. Okay, H of Z is equal to 0.2929 1 plus Z inverse whole square divided by 1 plus 0.1716 Z power minus 2. From this also you can understand that, so Z power minus 2 means it is a second order filter, and we have used a Butterworth filter approximation. So that is why it is a digital Butterworth filter. Okay, digital Butterworth filter transfer function. Okay, so like this, finally, so we have to conclude the problem. So in this way, so problems we have to solve whenever the problem is given like this, just to understand what is stop band cutoff, stop band frequency, pass band edge frequency, stop band attenuation, pass band attenuation. According to that, you use the equations to get the filter transfer function. Another way of calculating the filter order is there, n greater than or equal to. So this is completion of the problem. Okay. Now I will just briefly for 1 minute I will talk about this. N greater than or equal to log a divided by log 1 by k. Okay. Where a is equal to lambda by epsilon. See, lambda we have seen by epsilon, and that is equal to 10 power 0.1 s minus 1 divided by 10 power 0.1 alpha p minus 1. This alpha s is the stop band attenuation. Okay, stop band, S for stop band. Okay, stop band attenuation. Okay, this alpha p is the pass band attenuation. Okay, pass band attenuation. Because see, suppose if lambda and epsilon are not given, If it is not 0.707, something like you are given, assume that stop band attenuation is given 20 dB, pass band attenuation 0.4 dB. Like this, if it is given, directly we can use this formula to find out what is A. K is the omega p by omega s. However, this omega p, so omega p is pi by 2, omega s is 3 pi by 4. Like that. So using this A and K also you can calculate the order. So it is based on the problem description. If the problem description is given like this, you have to identify what is 1 by under root 1 plus lambda square, 1 by under root 1 plus epsilon square. From that we can calculate the order. Suppose pass band attenuation alpha p, alpha s is given, we have to use this formula. There is no other option, right? So directly we can calculate. It is simple. Calculating order using that lambda and epsilon is somewhat, you need more calculations. Here it is simple, directly these are available, omega s and omega p, directly you can substitute and we can find out the digital filter transfer function in this way. Okay, like this you can try for more problems. Such type of problems only appear in the university examinations. Okay, so in the next class I will give you 2 or 3 problems as a homework. You try it at your home. If there is any difficulty, we will see it later. In the next class we are going to see Chebyshev filter design. Okay, thank you.